On October 3rd, 2025, something very unexpected happened near Mars. It was supposed to be just another flyby, another dataset in the long list of comet observations. But when 3I Atlas finally enters the Martian vicinity, the world's leading scientists suddenly find themselves face to face with extraordinary anomalies. They expected it to behave like a normal space rock, moving smoothly, releasing some gas, and continuing its journey through the solar system. But that's not what happened. Instead, this mysterious object began acting in ways no one could fully explain. And the more scientists looked into it, the stranger it became. 3I Atlas travels along a hyperbolic orbit at more than 26 kilometers per second, meaning it will never return to the solar system. Astrometric analyses show that the object experiences negligible, non-gravitational acceleration. An upper limit on outgassing forces corresponds to a non-gravitational acceleration less than 3 times 10 to the minus 10 astronomical units per day squared. Combining that limit with dust and gas production measured by the James Webb Space Telescope gives a lower limit on the nucleus mass of 3.3 times 10 to the power of 16 grams and a diameter greater than 5 kilometers. The Hubble Space Telescope observed the comet in August 2025 and estimated the nucleus diameter between 440 meters and 5.6 kilometers, implying a wide range of possible sizes. These values dwarf the first two interstellar visitors. One, I Oumuamua, which is approximately 100 meters long, and two, I Borisov, which is approximately 1 kilometer. Orbit determination shows that 3I Atlas approaches the ecliptic plane at a shallow angle and passes near Mars, Venus, and Jupiter in sequence. Astrophysicist Avi Loeb notes that the chance alignment of a retrograde hyperbolic orbit with the ecliptic plane, allowing close approaches to multiple planets, is only about 0.2%, and the specific combination of passing within 30 million kilometers of Mars, 70 million kilometers of Venus, and 80 million kilometers of Jupiter. Kilometers of Jupiter drops the probability to around 0.005%. While most astronomers treat this as a coincidence, Loeb argues that the alignment is so unlikely that it warrants considering non-natural explanations, a concept we will revisit later. JWST made the first detailed spectroscopic observations of 3I Atlas on the 6th of August 2025 using its NIRS PEC instrument at a heliocentric distance of 3.32 astronomical units. The telescope's 0.6 to 5.3 micrometers spectra revealed a coma dominated by carbon dioxide with trace amounts of water, H2O, carbon monoxide, CO, carbonyl sulfide, OCS, water, ice, and dust. The measured CO to H2O ratio was 7.6 plus or minus 0.3, about 16 times higher than expected for a comet at that distance from the Sun. This ratio is among the largest ever observed in a comet and suggests one of two possibilities. Either 3I Atlas formed in a region of its home system near the CO2 ice line where carbon dioxide condenses but water remains gaseous, or its surface is covered by a thick insulating crust that prevents heat from reaching water ice deep inside. In either case, the low abundance of water relative to carbon dioxide is highly unusual. JWST found that gas production for CO2 and CO was confined within a few thousand kilometers of the nucleus, while water production might come from sublimating icy grains, leaving the total water output uncertain. Ground-based observations support the picture of a CO2-rich comet. Even at 6 AU from the Sun, when 3I Atlas was still near the orbit of Jupiter, NASA's TS and ESA's SPHEREX telescopes detected a coma roughly 23 kilometers in radius and an estimated nucleus radius of approximately 2.8 kilometers. The CO2H2O ratio of roughly 8:1, measured by SPHEREX and JWST, is consistent with a comet that either formed in extremely cold conditions or experienced surface processing that preserves CO2 and releases it preferentially. As 3I Atlas approached the inner solar system, the ESO Very Large Telescope's VLTU-VES spectrograph detected emission lines from neutral nickel NII and iron FEI. Observations between 3.14 astronomical units and 2.14 astronomical units showed that nickel atoms were present at all distances, while iron atoms were only detected when the comet was within 2.64 astronomical units of the Sun. The Nephi ratio was found to be an order of magnitude higher than the solar abundance and much higher than in other comets or in the interstellar comet. 2I Borisov. This extraordinary ratio decreases as the comet approaches the Sun. The authors propose that volatile carbonyl compounds, such as nickel tetracarbonyl and iron pentacarbonyl, could sublimate from the nucleus, releasing nickel and iron atoms. Yet even this mechanism struggles to explain why nickel is so abundant relative to iron. The debrief noted that such a high nickel production rate is puzzling because nickel and iron normally sublimate only at high temperatures. The finding has led some researchers, including Loeb, to speculate that the material might resemble industrial alloys. Loeb went further, suggesting that the detection of nickel without iron is only known from man-made alloys, hinting at a non-natural origin. Polarimetric measurements provide insight into particle sizes and surface composition by analyzing how light is scattered. Using the Nordic Optical Telescope, VLTFORS-2, and the Bulgarian Focal Reducer, Roshan 2 instrument, FORI-RO2, observers measured the degree of polarization of sunlight reflected from 3I Atlas at phase angles between 7.7 degrees and 22.4 degrees. They discovered a deep, narrow negative polarization branch with a minimum of -2.7% at a phase angle of 7 degrees and an inversion angle of 17 degrees. This combination of a steep negative branch and low inversion angle is unprecedented among known comets and asteroids. The slope at low phase angles resembles that of trans-Neptunian objects like Centaur Pholis, suggesting that 3I Atlas may have a red, ice-rich surface. Such extreme negative polarization hints at fine fluffy dust particles or unusual surface textures. And just before I get to the next point, if you're finding this video interesting, then make sure to subscribe to the channel and turn on notifications for more deep analysis and space exploration in the future. When the Hubble Space Telescope imaged 3I Atlas in late August 2025, observers expected to see a typical comet tail flowing away from the Sun. Instead, the image showed a bright glow extending sunward, often called an anti-tail, that was about 10 times longer than its width. Astrophysicists interpret this sunward extension as a jet of large ice fragments being launched from the comet's sun-facing side. Because the comet moves rapidly toward the inner solar system, these fragments can continue on nearly radial trajectories toward the Sun and remain in view longer than smaller dust particles that would be swept back into a conventional tail. Loeb lists this anti-tail along with the retrograde orbit alignment, large nucleus size, and CO2-dominated plume with nickel but no iron, as a collection of anomalies that may point toward something more than a typical comet. The anti-tail also suggests that the comet's outgassing is highly asymmetric. In September 2025, the Gemini South Telescope captured deep images of 3I Atlas that showed a growing coma and tail stretching across about 1/120,000th of a degree of sky. Scientists used the Gemini multi-object spectrograph to measure the colors of the coma and found that the dust and ice appear similar to those of solar system comets. The Gemini team emphasized that the colors and spectra of 3I Atlas suggest that the processes that form the planets of the solar system are common to other planetary systems. Thus, while 3I Atlas displays several unusual features, it also shares many properties with ordinary comets. Since Oumuamua's discovery in 2017, the possibility that interstellar objects might be technological artifacts has captured public imagination. Loeb argues that the combination of 3I Atlas's ecliptic alignment, retrograde, hyperbolic trajectory, sunward anti-tail, extreme nickel to iron ratio, CO2 dominated plume with little water, and strong negative polarization could indicate a non-natural origin, perhaps a long-defunct probe or fragment of alien technology. He points out that, unlike 1I Oumuamua, 3I Atlas is releasing gas and dust, making it easier to observe, and he encourages astronomers to search for radio emissions or artificial modulations in the spectrum. Loeb also notes that the comet's trajectory aligns within 5 degrees of the WOW radio signal's direction, although most researchers view this as coincidental. The high nickel content could result from sublimation of metal carbonyls formed in a cold, carbon-rich environment. The anti-tail could be produced by large ice chunks, and the retrograde, ecliptic plane trajectory might simply reflect the random distribution of incoming interstellar comets and a selection effect. Objects traveling near the ecliptic plane are more easily discovered by surveys. Observers note that 3I Atlas's colors and dust composition are similar to known comets, and that its CO2-rich composition might tell us about planet formation zones in other stellar systems, rather than about alien engineering. During the Mars encounter, the primary goal was to measure the comet's spectrum and search for temporal variations as the comet interacted with solar radiation. ESA's Mars Express and ExoMars TGO instruments attempted to detect spectral lines of CO2, H2O, CO, and other species by looking above the Martian atmosphere. Success depended on the comet's brightness and water content. The instruments might detect the halo and tail, but the nucleus would remain unresolved. Observations were complicated by the Mars-Sun-Earth geometry, which severely limited communication windows and forced the spacecraft to operate autonomously. As Earth's view was blocked, the task of monitoring the interstellar visitor shifted to an armada of Martian orbiters and landers. The Mars Reconnaissance Orbiter attempted to image the comet with high rise between the 1st and 4th of October, and HRSC and CASS were timed to capture the closest approach on the 3rd of October. Chinese and Emirati orbiters added additional perspectives, but as of writing, no high-resolution images have been publicly released. The lack of immediate data release has frustrated both scientists and enthusiasts. Nevertheless, once a full set of spectra and images is processed, they should help determine whether the comet's unusual chemistry changes when it is closer to the sun and whether the nickel to iron ratio and negative polarization persist. Observations may also reveal how much dust and gas were liberated during the Mars encounter and whether any sunward jets were active. Whatever 3I Atlas is, comet, spacecraft, or something entirely new, it has already changed how we think about space. It has shown us that the universe is full of mysteries, and we may only be scratching the surface. Could it be a visitor from another star system? A silent observer just passing by? Or is it nature showing us how little we really understand? We may not have all the answers yet, but one thing's for sure. This story is far from over. Stay curious and subscribe to the channel for more interesting exploration of deep space and the mysteries that are still lurking in the vast expanse of the universe.